load on beam. So you have a trapezoidal beam, it is in the shape of trapezium. And this is from our last lesson. This is UDL, UDL, uniformly distributed load. So it is ranging from 25 kilonewton per meter to 50 kilonewton per meter. So what you have to look for is the point load, which is acting on the centroid. So you have also to compute for centroid in this case. So we will divide this thing into two shapes. This thing are very simple, but I don't know why most students fear this. So I have the rectangular part and the triangular part. You see that? So I'll check for point load of the triangular part and then rectangular part. You get the point? So from this point to this point is 4 meters. So let's treat the triangular part be F1. So F1 is the area of the triangular part. Simple, that one, area 1. And area 1 is a half base height. So that is a half times base, which is 4, times height, which is 25, subtract from 50 is 25. So here up to here is 25 kilonewton. So that is times 25. Are we together? What do you get? Calc. 2. That is 50 kilonewton. Hapo sana. The triangular part, let's say it is acting here. That is 50 kilonewton. Let's go to the rectangular part. Let's give rectangular part F2, which is area 2, which is just length times height, which is, what do you have? 20, you have to here, 25 times 4, which is 100 kilonewton. So let's say for a rectangle is acting here. (100 kilonewton). Now, next thing is to get the centroid, because the whole trapezium is acting in the center. So you want to get the centroid. The centroid for trapezium. Let's say this is the centroid for trapezium. So the centroid for trapezium, point load for trapezium UDF becomes 100 plus 50, which is 150 kilonewton. I see. So here is around 150 kilonewton. So you want, let's say you are taking moment about B. Gives this one point B, this one is point A. So let's say this is reaction at RB, this reaction RA. Let's say you are taking moment about A. So you have to get the distance from here up to here. We call it centroid. So centroid is summation of F1x1 over summation of F1. You get that part? So let's get for the triangular part. That is, force for triangular part is 50 times the central for triangular part. If you have a triangular part, the centroid If you take it from the smaller end to the bigger end, it becomes 2/3 of the length. If you take it from the bigger end to the center or the centroid, you take it as 1/3 L. So we are going to take 2/3 L. Are you getting? So 2/3 of L is 4. What do you get? 8 divided by 3. It's 2.67 meters. So that is 2.67 meters. Are we together? It's Newton. Then this is kilonewton. Then we have for the rectangular part, force 100, right? Plus 100 times the central of rectangle is just a half of it, which is 2, right? Times 2. All together. So that is over the summation of the forces, which is 50 plus 100. What do you get here? 50 times this. 33.5 plus 200 over 150. What do you get? Add all of them, then divide by 150. Divide by 150. 2.22 meters. That is the centroid. 2.22 meters. Are we together? So we can apply the relations between moment about A is equal to, are we together? Or moment about B. Which one? Which is it? Moment about A or moment about B? So let's give moment about A. So it means RB is going to act what? Anti-clockwise, negative. Clockwise is positive. All together. So B is going to be anti-clockwise. Then the point load is going to be clockwise. Right together. So RB times the distance is 4 plus the point load is 36. So it is 150, right? 150 times the centroid. Let's take it about B because we have calculated the centroid to be from B, right? We have not calculated a third of from point B. So let's say RA. That one is RA becomes clockwise. Are we together? RA becomes clockwise times 4, then plus 150 times the central, which is 2.22, is equal to 0. So that one we have 4 RA and 150 times 2.2. What do you get? 333 is equal to 0. So we have 4 RA. Well, this is negative. That is negative. So RA is equal to 33 divided by 4. RA is equal to what? 83.25 kilonewton. Let's work for RB. So we are going to take the vertical components, that is summation of Fy is equal to 0. That is Ra plus Rb is equal to minus, these are vertical, minus 150 is equal to 0. Why do we say that? Because upward we take as positive, and downward we take as negative. So upwards are Ra and Rb, then point load becomes the downward. So Ra plus Rb minus 150 is equal to 0. What do you get? We are looking for Rb. Rb is equal to 150 minus Ra, and Ra we have is Rb is equal to 150 minus 83.25. What do you get as Rb? 66.75 kilo Newton. So the first thing, you divide the section into triangular part and rectangular part. Then you look for the point load. For example, you take the area of the rectangular part, you get the point load for the rectangular part. You take the area of the triangular part, you get the point load for triangular part. Then next, you get the central for this trapezium. Central, the formula is this. You get then central, we put it as bar x. So bar x is equal to summation of x1 over summation of f, which means all forces, moment about all forces, and total summation of all forces. That's what this one means. So we take the moment about triangular part plus moment about rectangular part, and then total forces. The point load for rectangular part and the point load for triangular part. Then you work out the central. After getting the central and you have the point load for the whole trapezoidal distributed load, then you can take the moment about B and work, and everything remains as usual.